So this is ELC 131, Circuit Analysis 1, and what we're going to talk about now is materials as they relate to magnetism. Now, we show a permanent magnet, and I again sketch the magnetic force that exists around this magnet. And I ask you, what happens when I place a piece of iron in proximity of this permanent magnet? Well, hopefully you all will answer that that piece of iron is pulled towards the magnet. That piece of iron is attracted to the magnet. That piece of iron is stuck to the magnet. And I ask you why. Why is it that that piece of iron is attracted to the magnet? Whereas if you placed a piece of aluminum close to that magnet, that piece of aluminum is not attracted to or stuck to the magnet. And the answer is really here. Permeability. Permeability is symbolized with the Greek letter mu, the same symbol we use for micro. And permeability is simply the measure of the ability of a material to establish flux. Now, when we discuss or describe or quantify the permeability of a material, we use this symbology, mu sub m, to represent the permeability of that material. And mathematically, it is the permeability of free space or a vacuum, mu sub O, times some relative permeability value. And this mu sub r depends upon the material. Now, the permeability of free space is 4 pi times 10 to the negative 7 Webers per ampere meter. And again, this is just a constant to quantify the ability for flux to be established in a vacuum or free space. Now, for example, the relative permeability of iron is 200. So what this tells you is that iron, it's 200 times easier to establish flux in a piece of iron than it is in the free space that exists beside the iron. So what we see happen is that this force around the permanent magnet will actually change its path to go through the iron because it's 200 times easier for the flux to go through the iron than it is to go through the space beside the iron. And again, remember these lines of force, this force are closed loops, and they go through the material as well as around the material. So these lines of force will be going in this direction inside that piece of iron, and that piece of iron is attracted back towards the magnet. Again, magnetic force going in opposite directions attracts. So that is why that piece of iron is attracted back towards the permanent magnet. Now, why is it that iron is attracted to a magnet and elements such as aluminum are not strongly attracted to a magnet? Well, it all has to do with atomic structure. Now we look at, again, the model of an atom. See the nucleus, electrons orbiting around the nucleus. And what I didn't talk about early this semester when we talked about atomic structure and charged bodies and current flow was that these electrons not only orbit around the nucleus, like the Earth around the sun, like the moon around the Earth. But these electrons also spin on their axis. That these electrons have what we call a magnetic moment. And this is, in some textbooks, referred to as a spin moment. So we look at this electron, and it's actually spinning on an orbit or on an axis here. And let's say, for example, this electron is spinning in that direction. So this electron will have a magnetic moment that is north to south. And the direction of the north to south pole of this magnetic moment of this particular electron is determined by the direction of its rotation. Now, with this particular atom, since it has 2 electrons in the outer orbit, this electron will have an opposite orbit. It will be spinning in the opposite direction, and it will have a magnetic moment south to north. These 2 magnetic moments cancel each other. So this chunk of material with these atoms in it, as it comes from the atom factory, will not have any resultant magnetic field. However, with elements like iron, because of their atomic structure, that an electron from a lower orbit is actually pulled up to the outer orbit when it's in proximity of magnetic flux. This is actually a d orbital electron in the lower subshell, for those of you that have taken chemistry. And this particular electron will have a spin moment that's aligned with this line of force, and will end up being south to north. And that's what makes this chunk of iron be pulled back towards the permanent magnet. It's all about atomic structure. Now, when we talk about materials with respect to or as related to magnetism, there are 4 categories of materials. One category or classification of material is ferromagnetic material. And ferro, from the Greek word for iron, these are materials that have very large values of relative permeability. They have a high ability to establish flux. And these materials are iron, nickel, cobalt, and alloys of those elements. And again, the reason that they have large relative permeability values is because of their atomic structure. They're able to, or they will, when in proximity to flux, pull a d orbital electron up from a lower subshell so that its spin moment or magnetic moment adds to those electrons in the valence orbit. Now, another category of materials are paramagnetic materials. And these are metals or elements or materials that have a permeability of slightly greater than 1. In other words, they are just very slightly attracted to a magnetic field. And an example of this, or the best example, is aluminum. If you've ever tried to pick up aluminum with a permanent magnet, you would see that the aluminum is slightly attracted to the permanent magnet. However, the attraction of the aluminum to the permanent magnet is not great enough to overcome the force of gravity. So included in our list of paramagnetic materials, of course, aluminum, barium, calcium, oxygen. There's a great many other number of elements and materials that fall in this category. Now, the third category of materials are diamagnetic materials. And these are the materials that have a relative permeability value of slightly less than 1. In other words, these materials are actually slightly pushed away from the flux. It's harder for flux to go through carbon than it is to go through the air beside it. So we would find if I put a piece of carbon here, that these lines of force would be slightly pushed away from the carbon. And in the list of diamagnetic materials, carbon, lead, mercury, copper, H2O, water, and sodium chloride. Again, there's many more materials in this list. And the fourth category of materials we have are ferrimagnetic materials. And these are actually, I didn't write it up here, I apologize. The permeability, the relative permeability is 10,000s, huge numbers of relative permeability. And these materials are made of alloys of iron oxides and materials such as manganese, oxygen, nickel, other materials. And what they do in forming this ferrimagnetic material is they make a powder of these oxides and they sinter them together, which means they're put together under great heat and great pressure to make a very lightweight material that has very high levels of relative permeability. And these materials are used quite often in magnetic devices such as speakers. One issue with the ferrimagnetic materials is that they are very brittle. So you have to take caution with these devices. Trust me, from my own experience, if you drop them, you'll have many pieces to deal with. So again, when we talk about materials with regard to magnetism, our key metric or unit of measure is permeability, the ability to establish flux. And we talk about the permeability of a material. It's always calculated by taking the permeability of free space times some relative permeability value. And for example, the relative permeability of iron is 200. And we classify our materials in these following classifications, or in the classifications shown, and it's all determined by atomic structure. That's why some materials are strongly attracted to magnetic fields. Some are weakly attracted to magnetic fields. Some are actually pushed away from or repelled from magnetic fields. And some materials have extremely high levels or values of relative permeability, and they're made of oxides of iron and iron oxide and other materials.